Hello! Today, we're going to dive into the powerful world of exponential functions and learn how to manipulate them. Our learning objective for this session, labeled 2.4a, is to be able to rewrite exponential expressions in various equivalent forms. This might seem simple, but mastering these manipulations is crucial for understanding how exponential functions behave and for solving problems. By the end of this video, you'll be able to confidently transform complex exponential expressions into simpler or more revealing forms. Let's start with our first property. By the end of this scene, you'll be able to use the product property to rewrite horizontal shifts of exponential functions. This is the product property, which states that when multiplying powers with the same base, you add the exponents. Mathematically, that's b to the power of m plus n equals b to the power of n times b to the power of n. This property allows us to connect two seemingly different transformations, horizontal shifts and vertical scalings. A horizontal shift moves the graph left or right, while a vertical scaling stretches or compresses it. Consider the function f of x equals b to the power of x plus k. The k inside the exponent causes a horizontal translation of k units. If k is positive, it's a shift to the left. If k is negative, it's a shift to the right. Now, let's see how we can rewrite this using our product property. We can separate the exponent. X plus k becomes x plus a constant k. So, we can rewrite b to the power of x plus k as b to the power of k, multiplied by b to the power of x. Notice that b to the power of k is just a number. Let's call it a. So, our function becomes a times b to the power of x, where a is a constant multiplier. This means that any horizontal shift of an exponential function can always be rewritten as a vertical scaling. The amount of the shift determines the scaling factor. Now you can use the product property to rewrite horizontal shifts as equivalent vertical dilations. Let's work through an example. In this scene, you'll be able to apply the product property to rewrite an exponential function. Consider the function f of x equals 2 to the power of x plus 3. Without changing its form, this function represents the graph of 2 to the x shifted 3 units to the left. Remember, an addition inside the exponent causes a shift in the negative x direction. We can rewrite this using the product property. The exponent is x plus 3. So we can split it into 2 to the x times 2 to the 3. Now we can simplify 2 to the 3. 2 cubed is 2 times 2 times 2, which equals 8. This means our function f of x can be rewritten as 8 times 2 to the x. In this new form, we can see that our function is now a vertical dilation of the parent function, y equals 2 to the x, with a scaling factor of 8. The original left shift of 3 units is mathematically equivalent to a vertical stretch by a factor of 8. Now, let's move on to our second key property. Your objective here is to learn how the power property allows you to change the base of an exponential function. This is the power property. It states that when you raise a power to another power, you multiply the exponents. So, b to the m, all raised to the m, is equal to b to the m times n. This property is essential for dealing with horizontal stretches and compressions. A horizontal stretch or compression occurs when you multiply the input x by a constant c. For an exponential function f of x equals b to the power of c times x, the input x is multiplied by c. If c is greater than 1, it's a horizontal compression. If c is between 0 and 1, it's a horizontal stretch. Now let's see how we can rewrite this. The exponent c times x can be written as an inner exponent of c and an outer exponent of x. So, using the power property, b to the power of c times x is equivalent to the quantity b to the power of c, all raised to the x. Let's call this new quantity b to the c our new base, which we'll call a. Our function now takes the form a to the x. This is a profound realization. A horizontal stretch or compression of an exponential function simply changes the function's base. The entire graph is rescaled in such a way that it looks like a standard exponential function with a new growth or decay factor. You have now learned how the power property helps you change the base of an exponential function in response to a horizontal dilation. Let's put this into practice with an example. Your goal here is to be able to use the power property to rewrite a horizontal dilation. Consider the function f of x equals 25 to the power of 0.5x. The 0.5 in the exponent represents a horizontal stretch by a factor of 2. We can rewrite this to see the equivalent change in the base. We'll apply the power property, grouping the 0.5 with the base 25, This gives us the quantity 25 to the power of 0.5, all raised to the x. Now we need to simplify the new base, 25 to the 0.5 power. Remember that a power of 0.5 is the same as the square root. The square root of 25 is 5. This simplifies our function to f of x equals 5 to the x. So, our function, which was originally a horizontal stretch of y equals 25 to the x, is mathematically identical to the function y equals 5 to the x. The horizontal stretch by a factor of 2 is equivalent to changing the base from 25 to 5. Next, let's explore what happens when exponents are negative. In this scene, you will learn the negative exponent property and its connection to exponential decay. The negative exponent property states that a term with a negative exponent is equal to its reciprocal with a positive exponent. So b to the power of negative n equals 1 divided by b to the power of positive n. This property is incredibly useful for rewriting expressions and can provide a new perspective on exponential decay. Consider the function f of x equals 10 to the power of negative x. Because the base is greater than 1 and the exponent is negative, this represents exponential decay. We can rewrite this using our new property, the exponent is dash x. We can rewrite 10 to the power of negative x as 1 divided by 10 to the power of positive x. This is the reciprocal, and you can see that as x gets larger, the denominator gets larger, so the overall fraction gets smaller, confirming decay. Alternatively, we can think of this as applying the power property first. The exponent dash x is the same as negative 1 times x. This means we have the quantity 10 to the power of negative 1, all raised to the x. And what is 10 to the power of negative 1? It's its reciprocal, 1/10. This shows us that negative exponents are connected to reciprocal growth or decay. An exponential function with a base b and a negative input exponent is equivalent to an exponential function with the reciprocal base, 1b. You have now mastered the negative exponent property, a powerful tool for rewriting expressions and understanding decay. Finally, let's explore our last property, which connects exponents and radicals. In this scene, you will learn to rewrite fractional exponents as radical expressions and vice versa. The fractional exponent property states that a fractional exponent is equivalent to a radical. Specifically, b to the power of 1 over k is equal to the kth root of b. The denominator of the fraction, k, tells you the root to take. For example, a power of 1/2 is the square root, and a power of 1/3 is the cube root. This property extends to any fractional exponent. b to the power of m over k can be written as the kth root of b to the power of m. Alternatively, you can take the kth root of b first, and then raise the result to the power of m. Both of these forms are equivalent, and the best one to use often depends on the specific numbers in the problem. Sometimes it's easier to find the root first, especially if the base is a perfect kth power. Let's look at an example, 125 to the power of 2/3. Using the power property, we can rewrite this as the quantity 125 to the power of 1/3, all raised to the power of 2. The 1/3 exponent is the cube root. The cube root of 125 is 5, so this simplifies to 5 squared. And 5 squared is 25. By rewriting the fractional exponent, we were able to simplify the expression significantly. You have now learned how to use the fractional exponent property to connect exponential functions to radicals, allowing for more ways to rewrite and simplify expressions. Now, let's bring everything together with a more complex example. Your objective is to rewrite a multi-step exponential expression in its simplest form. We're asked to rewrite the function f of x equals 16 to the power of 1/2 x minus 3. We can see multiple transformations here. First, let's use the product property to separate the subtraction and the exponent into two separate terms. This gives us 16 to the power of 1/2 x multiplied by 16 to the power of negative 3. Now we can simplify each of these two terms. Let's start with 16 to the power of 1/2 x. We can use the power property to change the base. 16 to the 1/2 x is the same as the quantity 16 to the 1/2, all raised to the x. And 16 to the power of 1/2 is the square root of 16, which is 4. So the first term simplifies to 4 to the x. Now let's simplify the second term, 16 to the power of negative 3. We'll use the negative exponent property. 16 to the power of negative 3 is equal to 1 divided by 16 to the power of positive 3. 16 cubed is 4,096. So the second term simplifies to 1 over 4,096. Now we just need to put our two simplified terms back together. Our function f of x is equal to 4 to the x multiplied by 1 over 4096. We can write this as 1 over 4096 times 4 to the x. In this final form, it's clear to see the base is 4, and there's a vertical scaling by a factor of 1 over 4096. This single form captures all the transformations of the original expression. You have successfully rewritten a complex exponential function using all three properties. Let's quickly recap what we've learned. In this final scene, your objective is to be able to summarize the key strategies for rewriting exponential expressions. We covered 4 essential properties for manipulating exponential functions. First, the product property, b to the m plus n equals b to the m times b to the n, allows you to rewrite horizontal shifts as equivalent vertical scalings. Second, the power property, the quantity b to the n equals b to the m times n, helps you rewrite horizontal dilations as an equivalent change in the base of the exponential function. Third, the negative exponent property, b to the negative n equals 1 over b to the n, connects negative exponents to the concept of reciprocals, which is crucial for understanding exponential decay. And fourth, the fractional exponent property, b to the 1 over k equals the kth root of b, connects exponential functions to radicals, giving you another way to simplify expressions. Remember the key takeaway. Understanding these properties allows you to see the same exponential function in different forms, each highlighting a different aspect of its behavior. You have now learned how to rewrite exponential expressions in equivalent forms, achieving our initial learning objective.